Hello everyone, Dr. Hasbullah here, and in this video we are going to be looking at a few examples about the energy equation. And for the first example, what we have here is a pump that is going to deliver water at the flow rate of 0.2 meter cube per second. Okay, and this is a pump. So we know that in our energy equation, we will have this term HP. Okay, and what we have next is that the outlet is 20 centimeter higher than the inlet. All right, so the flow comes from left to right, and the pressure here is at 200 kilopascal. And when the flow goes through the pump, the pressure has increased to 600 kilopascal. And the next information that is given to us is that the area of the inlet is equal to the area of the outlet. And for this problem, what we are really looking for is the power that the pump requires in order to deliver this fluid. And I believe that from our previous video, the pump power is defined as this equation. So let me write this again. The pump power, W dot P, is equal to gamma QHP over eta P. And eta P is the pump efficiency, and eta P is actually given, and eta P is equal to 85%, meaning that this pump has 85% efficiency. Now, first of all, let me write the equation again. So this is the energy equation, HP plus V1 square over 2G plus P1 over rho G plus Z1 equal to V2 square over 2G plus P2 over rho G plus Z2 plus HT plus losses. And I know that in my problem, the first thing that I'm going to cancel out is actually HT because we have no turbine here, and also we assume no losses because there are no information that's given to us that indicate that there are any losses in here. The next thing that I can cancel out is actually based on this information. When A inlet is actually equal to A outlet, remember that in steady flow, right, Q, which is equal to V1 A1, will equal to V2 A2. So what happens when A1 is equal to A2? It means that V1 is also equal to V2. So I can easily cancel this out. And remember, I need HP in order to solve this equation. So what is my HP? HP is equal to P2 minus P1 over rho G plus Z2 minus Z1. And P2 minus P1 is simply 600 kilopascal minus 200 kilopascal. So 600,000 minus 200,000. And then divide by rho G. So this is 9810 plus Z2 minus Z1. The difference is 20 centimeter. And 20 centimeter in meter is 0.02 meter. Now, let's find out what is the HP. So, this is 600,000 minus 200,000 divide 9810 plus 0.02. That is about 40.8 meter. Okay, and this is what we call the pump head. It's not the pump power yet, but it is pump head. So, to get W dot P, I'm just gonna write again this equation. W dot P is equal to rho G Q HP over eta P, which is 9810 times Q. Our Q is 0.2 meter cube per second. Our HP is 40.8 and our eta P is 85%. So this is 0.85. And if I calculate again, 9810 times 0.2 times 40.8 divide 0.5. This is 94176 watt. Or we can write it as 94.18 kilowatt. And that is our answer for this question, because the question only asks us for the power that is required by the pump. And this is how you get it. First, write the equation and then determine what can be cancelled out, and then look for HP, and finally look for the power. Now let us move on to our next example. So this is example number 2. And if example 1 has pump, for example number 2 you have turbine. Okay, so this is a water pipe that goes inside the turbine, and this is connected to the river. And at the upstream is the reservoir. So this is likely a dam. So this is reservoir and this is river. And this is the water level for the river, and this is the water level for the reservoir. And this is your turbine. So of course the fluid will flow from left to right. This is from reservoir into the river. And of course when the fluid goes through the turbine, it will generate power, isn't it? So I think you can guess what the question is looking for. That is of course the turbine power. But what are the information that's given to us? First, we have diameter of this pipe, which is 0.8 meter. And then we know that the river is actually 30 meter below the surface of the reservoir. And it's also given to us that the flow rate Q is equal to 3 meter cube per second. And the turbine efficiency, which is eta T, is actually 88%. Now, when you look at this problem, okay, first of all, we know that the scale is huge. First, notice that the elevation is 30 meter. 30 meter is like a 10-story building, okay? And then, the pipe is 0.8 meter. 0.8 is a big pipe. And also, the flow rate is 3 meter cube per second. 1 meter cube is already a lot. 1 meter cube is 1,000 kilogram of water. So 3 meter cube means that 3,000 kilogram of water is going through this pipe per second. So you know that the scale of this is huge, and you can expect that the power will be large as well. It's got to be hundreds and hundreds of kilowatts or even megawatts. But before that, let's see how we can solve this equation. Right? First step is to write the equation HP plus V1 square over 2G plus P1 over rho G plus Z1 equal to V2 square over 2G plus P2 over rho G plus Z2 plus HT plus HL. L is losses as usual. And what is W dot T? Okay, so the power of the turbine, as we've seen in our previous video, is actually this equation. Okay, so that will be gamma Q HT eta T. Right, so let's write this again here just for our reference. So we are looking for W dot T, which is gamma Q HT eta T. And of course, what we have now is eta T. I think we have Q and we also have gamma. And what we really need now to solve this equation is just HT, and we are going to get HT from this equation. But first of all, let's take a look at what are the terms that we can cancel out. First of all, of course, this problem only has turbine, so no pump whatsoever. And let's define our point 1 and point 2. So this is our point 1 and this is our point 2. So we now know that Z1 minus Z2 is equal to 30 meter, right? So what about V1 and V2? Okay, when you place point 1 at the surface of the water, imagine a dam, right? It's a large body of water. V will be the velocity of that point going down as the water drains from the dam. And it is safe to assume that this velocity is actually zero because it is just too small. It is just too long to wait for the dam to drain. So velocity is 0. And I can cancel this out. And the same goes to the river. The velocity that goes up and down on the river surface is very small, so we can neglect that as well. And what happens to pressure at point 1 and pressure at point 2? Now, pressure at point 1 is atmospheric pressure and pressure at point 2 is also atmospheric pressure. So, P1 and P2 can be cancelled out. And you are left with Z1, Z2 and H loss. There are actually a few information about H loss. The question gives you information like K equal to 2, and if you remember, HL is actually kV square over 2G. So definitely HL is inside this pipe. So the losses are occurring inside this pipe. Because when you say that HL is equal to kV square over 2G, we already assume that V at the reservoir is 0 and V at the river is 0. So the only logical V here is the velocity inside the pipe. Okay, so let's see what HT looks like now. So HT is Z1 minus Z2 minus HL. And Z1 minus Z2, we know that this is 30 meter. Okay, it's here. And what about HL? So this will be minus kV square over 2G. And this is 30 minus K is 2. And V, what is V? We know that in order to get V, we need to use Q. So Q is velocity times area. Velocity is Q divided by area. So what is our Q? Q is 3 meter per second. And area is pi times diameter is 0.8. 0.8 square divided by 4. Okay, so you end up with velocity of 3 times 4 divided by pi divide 0.8 square. This is 5.97 meter per second. So this will be 5.97 square. Don't forget the square. Divide by 2 times 9.81. This will be square times 2. Divide by 2. Divide by 9.81. 30 minus answer. That will be 26.37 meter. And once we get HT, we can solve this equation definitely. So W dot T, I'm going to write it again. W dot T is equal to gamma QHT eta turbine. So this will be 9810. Q is 3 meter per second, 3 meter cube per second. HT is 26.37. Eta is 0.88. And this is equal to 9810 times 3 times 26.37 times 0.88. This is equal to 682.9 kilowatt. And this is our answer for this question. The question asks for the power that the turbine produces, and the power that we found is 682.9 kilowatt. We already assumed that this power is going to be huge. I've told you before that it's going to be hundreds of kilowatts or even megawatts. So now when we get 682.9 kilowatt, it's got to be the correct answer for problems that are in this scale. And now we are going to be moving on to our next example, which is example number 3. And for example number 3, you have a device that is called a Venturi meter. A Venturi meter is a device that has different cross-sectional area. So the flow comes from the bigger cross-section area, and then the area becomes smaller, and then it becomes big again. And usually we use Venturi meter in order to get the mass flow rate. Right? So Venturi meter looks something like this. And you have a manometer that is measuring the pressure difference between the larger cross-section and the smaller cross-section of this Venturi meter. And the manometer looks something like this. And then you have mercury inside this manometer, and the mercury sits over there. And the distance between this and this is 1.2 meter. This is mercury. Now let's draw our control volume first. Our control volume looks something like this. So this will be our inlet and this will be our outlet. And I'm going to label this as V1 and this is V2. And the question is asking you to find what is the mass flow rate. Okay, so mass flow rate of the fluid that is inside this Venturi meter. And what's given to you is just the pressure difference between point 1 and point 2. And if you notice, velocity is not given. But remember that in the energy equation, velocity is there, but velocity is not given here. So let's see how we can solve this equation. And remember, we are looking for m dot. And of course, the equation for m dot is rho times velocity times area. Now it seems like we have rho and we actually have area. So area here is 100 millimeter and the area here is 50 millimeter. So we also have area. Now, what is our velocity? So first of all, I'm going to write the energy equation. So this is HP plus V1 square over 2G plus P1 over rho G plus Z1 equal to V2 square over 2G plus P2 over rho G plus Z2 plus HT plus H losses. Now, obviously, there are a few parameters that we can immediately cancel out, which is HP, we have no pump here, and we also have no turbine, and we're also going to assume that losses is 0. And we can also cancel out Z1 and Z2 if I were to draw the center line of this pipe here. Okay, so point 1 and point 2 should be there. So Z1 and Z2 is 0. And you are left with this equation. 0 equal to V2 square minus V1 square over rho G plus P2 minus P1 over rho G. I'm sorry, this is 2G. Now, when we are left with this equation, I believe now that with the help of the manometer, we can actually find what is P2 minus P1. And if I label this to be Z, or I'm going to label this as H, for example, okay? And what I will do is that I'm going to move from point 1, I'm going to move it down and go here, go down, and then go up and up again to find pressure at point 2. So P1, and of course when we go down, we're going to use plus. So plus, this will be rho GH. So this is rho water. GH is H. So this is here. And then I'm going to go down one more time. But this is at 1.2 meter. So this is plus rho water times G times 1.2 meter. And I can jump here and go back up. So this will be minus, this time rho HG times G times 1.2. And I'm going to go up again to 0.2. And this is minus rho water GH equal to P2. And remember, we are looking for P2 minus P1. So P2 minus P1 is actually rho water times G. This is H plus 1.2 minus H minus rho Hg times G times 1.2. And H minus H is 0. So this will be rho water times G is 9810 times 1.2 minus rho Hg is 13,600 times G is 9.81 times 1.2. This will be 9810 times 1.2 minus 1,600 times 9.81 times 1.2. This is minus 148,327 Pascal. So 148 kilopascal is actually quite high. So I suspect that the mass flow rate will be high as well at the end. And is it true that this is negative? Okay. Now, remember that we are looking at P2 minus P1. So P2 is at the smaller section of the pipe. So the flow area goes from large to small area. And what happens when the flow goes from large to small is that the velocity will increase. And Bernoulli says that when velocity increase, pressure will decrease. So you can expect that pressure at point 2 is lower than pressure at point 1. That's why when you have here P2 minus P1, you will have negative values. So I think our value here is correct. And we can plug it in here and find the velocity. So 0 is equal to V2 square minus V1 square over 2G plus, and this is minus 148,327 divided by 9810. Okay, but still we have V2 and V1 and we need to solve for this, right? So what is the relationship between V1 and V2? We know that the flow rate is the same between inlet and exit. So Q is equal to V1A1 is equal to V2A2. And if I take V2 here, so V2 will be V1A1 over A2. And A1 over A2 is pi D1 square over pi D2 square times 4 over 4. So this cancels out. And this can cancel out as well. And D1 is 100 millimeter and D2 is 50 millimeter. So this will be V1 times 0.1 square over 0.05 square. And you will end up with 4V1, right? So V2 is actually equal to 4V1, and if I want to plug it into this equation, so let's write that equation again. 0 is equal to 4V1 square minus V1 square over 2G minus, so I'm gonna solve that, 148,327 divide 9810, 15.12. Looks like we're going to end up with, this is going to be 16 V1 square minus V1 square over 2G minus 15.12. This will be 15 divided by 2, 7.5 V1 square over G minus 15.12, and V1 will be 15.12 times 9.81 divided by 7.5, square root of that is 4.45 meter per second. And that is your V1. And now, do we have everything that we need in order to solve the mass flow rate equation? Remember that mass flow rate is rho times velocity times area. It doesn't matter whether it's at point 1 or at point 2 because both of them will be similar. Alright, I think we're going to have it at point 1. So m dot is equal to rho 1 V1 A1. Rho is of course 1000 times V1 is 4.45 and A1, again the diameter at point 1 is 100 millimeter, that is 0.1 meter, pi times 0.1 square over 4. And our m dot will be times pi times 0.1 square over 4 times 1000. That will be 35.0 kilogram per second. And that is our mass flow rate that is going through this Venturi meter. Okay, so the mass flow rate there is 35 kilogram per second. Remember that we noticed before that our pressure difference seems a little bit large here. So because we have this pressure difference to be so large, we suspect that the flow rate will also be large. And then we find out that the flow rate is 35 kilogram per second. So 35 kilogram of water every second. That's a lot of water, right? So I think that this value of mass flow rate is correct. So now we have answered this problem where we need to find the mass flow rate. And remember, it's all originated from this energy equation. The rest is just you solving the manometer and then solving the V1 and V2 and find the relationship between them. And finally, you get the mass flow rate. So energy equation is very important and it's better for you if you remember it. It makes it easier for you to recall when solving questions. Okay, everyone, so those are 3 examples for you, 3 very different examples, but we use similar equation, which is energy equation, in order to solve all of that. I hope you can see that this energy equation can be used across many engineering problems. So it's important for you to do this example again and again until you can do it without even looking at the solution. With that, I think that is all from me for now, and I'll talk to you soon. Bye.